Hello, and welcome to a video lecture on nonlinear material and plastic deformation. In your design experience up till now, you have probably focused on small displacements and remaining in the elastic region for your designs. However, in many applications, engineers actually design in the nonlinear material region, and in particular they allow some portion or some amount of plastic deformation in the design because it significantly reduces the size of the members that are needed. And so that's what we're going to focus on in this section is learning how to design by allowing desired amounts of plastic deformation. And we're going to look at the models that we use and the theory that we follow to come up with these equations and do this analysis. This title slide shows a few photographs of some interesting designs. First of all, here we have a solar-powered spacecraft or aircraft designed by NASA, and you can see the extremely large elastic deflection in the aircraft. I don't think this was intended because a few slides later or photographs later, this aircraft ends up in the ocean due to wing failure. Here's another unfortunate failure. We can see that the pole bent. It's kind of interesting to think about if the pole broke in the locations you would expect and in the where the moment would be the largest. Here's an extremely catastrophic failure. It's a loading dock. You can see the size of these members and columns compared to a person and all these vehicles down here. So this thing is extremely large, and these large beams have just completely bent over and broke and failed in a plastically deformed manner. Here's another beam that has completely bent around and failed. We see that it hasn't really cracked or broken apart, but all of these, well, these two show plastic deformation type failures, where this one shows a fracture type failure. So there's a difference in those, and these are some of the things we're going to talk about in this section. To start with, we're going to talk about inelastic material behavior and review a few concepts that you've seen earlier, but we'll refresh these ideas so that we understand what's going on with plastic deformation. Here it talks about the limitations of a uniaxial standard stress strain data or test. This would be a tensile test in a machine where we're simply pulling on the test specimen to get a stress strain curve or a load deflection curve, and then extract the modulus of elasticity, yield strength, and so forth. In these types of tests, the load rate is extremely important because the material acts so differently based on the strain rate or the load rate. And we learn here that a typical tension testing machine and load rate is in the range of 0.2 to 10 millimeters per minute. And this would be at room temperature. Now, there are standards and codes that have been published that state the sizes, rates, and the environmental conditions that must be followed while doing a tension test or a material stress strain test. And one example of these standards is the ASTM specification A370. And this provides the definitions of mechanical testing of steel products. And there are several of these testing standards produced by ASTM. And there's also other test standards outside of ASTM that can be followed. It's kind of interesting to give a little bit of history about ASTM. In 1898, a guy named Dr. Charles B. Dudley, who was a chemist with the railroad in Pennsylvania, founded the American Society for Testing of Materials. And then this grew into what it is now, which is extremely large with over 12,000 standards, and they operate worldwide. In 2001, the name was changed to ASTM International, and this website here, astm.org, you can go and find all of these standards. So like I said, this is published by ASTM, and they state that over 12,000 ASTM standards operate globally. And these standards are defined and set by them, and that they have improved the lives of millions of people and every day. They state that it's combined with our innovative business services. ASTM standards enhance performance and help everyone have confidence in the things they buy and use, from the toy of a child to the aircraft overhead bins. So there are an extremely large range of ASTM standards. It's interesting, I have done a fair amount of accident reconstruction, failure analysis, product failure analysis, and typically you can find an ASTM standard for about any failure that you're investigating. For example, there are standards for designing treadmills. There are standards for testing tooth whitening strips and the plastic that is used in those. There are standards for tensile testing, and there are standards for child toy products. I've also used ASTM standards to design overhead bins in aircraft. So there's just an extremely large range of these standards. And as an engineer, if you are designing a product, you want to make sure you do a standards search so that if there are standards for the product you are designing, that you are meeting those standards. These standards are available online. They cost in the range of 50 to 150 US dollars. And like I said, I have purchased several of these over the years, and I provide a portion of ASTM D882-97 in the appendix of your note packet, which would be the very last packet that's provided. So we're going to discuss some of the conditions in the tensile testing standards in the following pages. So the limits of properties obtained from typical tension tests depend on several variables of the test, and we're going to talk about some of those now. The first one we're going to talk about is the load rate. A slowly loaded ductile material typically has a linear elastic region and then transitions into a non-linear plastic region. And you've all seen this before. This is kind of what we're used to. But if the load rate becomes higher, then the material does not have as much plastic deformation, and the failure load is reduced. So the yield strength and the modulus elasticity can be increased and really over predicted if the load rate is fast. The material appears to be less ductile than it really is. And if the load rate becomes so high that it appears like it's an impact load, then there won't be any plastic deformation at all because the material can't respond that quickly, and the material will act like a brittle material. On the extreme other hand, if the load rate is too slow, the modulus of elasticity and yield strength will appear to be less than in a conventional test. So load rate could probably be the most important part of a tension test and can affect the results a lot. Another property or part of the test is the temperature. We know that in low temperatures, many materials will act like a brittle material, where there is just a little bit of plastic deformation before failure. In metals, plastic deformation at room temperature occurs by motion of dislocations. And we'll talk a little bit about those dislocations and review some things. The stress required to move a dislocation depends on the atomic bonding, the crystalline structure, grain boundaries, precipitate particles, and other dislocations. And if the stress required to move the dislocation and have plastic deformation is reached, cracks develop and the material will fail due to the crack propagation, and the failure will be brittle. Now again, with temperature, if we have body-centered cubic BCC materials, they exhibit what we call a ductile to brittle transition temperature. And these most low-carbon steels are included in this BCC crystalline structure type of material. And here's kind of what happens. If we look at impact energy, so the ability of the material to absorb energy, if we have a high temperature, then our material will be ductile, and it will be able to absorb a high amount of impact energy. Down at low temperatures, these materials have very little ability to absorb energy, and they just fracture and break. And then there's a range where we have what we call the ductile to brittle transition temperature, and it's the temperature range where we go from the high to the low. And it's important to note then that this ductile to brittle transition temperature occurs in body-centered cubic crystalline structures. If we review our crystalline structure ideas a little bit, we see that this image here is an image of face-centered cubic materials, and we're looking at the atom's cross-section right here on the face. And then in the body-centered cubic, we actually have the atom in the middle of the structure. And then another very common crystalline structure that for metals is this hexagonal close pack that looks like this. Now in face-centered cubic materials, the force required to move the dislocations is not strongly temperature dependent. And so FCC materials remain ductile even at low temperatures, whereas BCC materials do have a significant change in their material properties based on temperature. Here's kind of an interesting table. It shows us the element, and then it shows us the crystalline structure. And so we can see that all of these FCC materials would not have a temperature, a significant effect on the material properties based on temperature. And it's interesting to note that lead is involved in here, nickel is involved, gold, copper, but probably the most important would be aluminum. And it's interesting to note then that aluminum, being face-centered cubic, will will not have a significant change in its material properties due to a temperature change. However, when we come down here and look at iron, we see that it is body center cubic, and we look at molybdenum and its body center cubic. And so these materials will have a significant change in their material properties based on temperature. Kind of an interesting plot. Along with temperature, we considered low temperature and the effects that it has by reducing the impact energy and the ability to absorb energy. High temperature also has an effect, and high temperatures typically increase ductility. However, under very high temperatures, we get recrystallization, and if the load is continuously applied to the material, it will continue to plastically deform until failure occurs. And this continued plastic deformation at high temperatures is called creep. So it's important to note that once you hit the recrystallization temperature, it's actually much easier to bend and plastically deform the material. And most of you have experienced this by a cutting torch or heating a material to bend it. Once we get it glowing red, which is an indication of the recrystallization temperature, then the material folds and bends quite easily. The next step, or the next parameter, is load reversal. And this image kind of shows what we're talking about here. It says that if a material is loaded into the plastic region and then unloaded, the unloading path does not follow the ideal linear model that we have been assuming. It's noted that the compressive yield strength has been significantly reduced, and we can see that in this plot below. Here we started to load the material, we had a linear region, and then we started to become nonlinear through here, and we had some plastic deformation, because when we unloaded the material back to zero, we had this much permanent set, or this much permanent strain in the material. Then as we continue to push the material into compression, we can see here that we have a much lower slope line than up here, and we hit this 2% strain, or 0.2% strain, and our yield strength in compression would be much less than the yield strength in tension. And we can see that here, where this point C would represent this point A up here, kind of in the area of our yield strength, where our yield strength here is on the order of half of that value. Then as we continue to push it in compression, you can see that we get a very large deformation down in this region here, and all of this would be a plastic deformation. So this is kind of an interesting plot to show how a material, due to a load reversal, does not respond exactly how we've been assuming it does in our previous models. If we look at multi-axial loading, so we're pulling on this in various directions, plastic deformation can occur in materials due to torsion, tension, compression, and a combination of all of these, and in multiple directions, even though one single stress by itself does not predict plastic deformation. So what happens is the coupling of torsion, tension, compression, these stresses here individually are not large enough to cause plastic deformation, but when they're combined in a structure, they can become large enough. And so it's important that when we have multi-axial loading, or multiple loads, that we use the distortional energy failure theory that you talked about in your machine design class. Because this distortional energy failure theory represents the complete stress state, or represents all of the stress components that occur in the model or in the structure at that point. And so when we do include or account for all those different types of stresses, what we usually end up computing is what we call the von Mises stress. This is also called sigma prime. In some finite element codes, it's called the equivalent stress, such as ANSYS. Now we want to talk about nonlinear material response. And there are kind of four models or four cases that develop in a nonlinear material response, and we're going to talk about each one of them. These photo or pictures below come from your textbook. This is figure 4.2 in your textbook, so chapter 4, figure 2. And if we look at this, we can see that the first model is what we would call nonlinear elastic. And so we are linearly elastic up to this region, and then as we continue to load, we go nonlinear. And then as we unload, we follow this line right back down. And so there's no plastic deformation, and we are nonlinear. So this would be a nonlinear elastic model or material. The next case is what we would call plastic. Here, as we load the material and we go into the nonlinear elastic region, we know that it becomes plastic in here somewhere, because as we unload, we have this much permanent strain or plastic deformation. So this is a case that when we start to become nonlinear in here, then we go plastic, because when we unload it, that's about the amount of plastic deformation that we have. The next case is what we would call viscoelastic. And in this case, we load up the material, we go nonlinear, and then as we unload, we have some plastic deformation. But over time, we see that this goes back to zero, making it viscoelastic. The visco essentially means that this is a relatively slow process and doesn't follow the line right back down. It takes some time after the unloading for the deformation to get back to zero. That's viscoelastic. Then we have viscoplastic, and in this case, our material is loaded, it's loaded up into the nonlinear region. Then as we unload, it goes back down and we have some permanent set, but we also have some viscoelastic effect. And so if this does not go back to zero, we call it viscoplastic, because we have some permanent set here, as compared to the viscoelastic that did go all the way back to zero. So these are the four nonlinear material response models that we should be aware of throughout this analysis. If we continue talking about stress-strain curve models, experimentally, materials usually follow either this type of a stress-strain curve or this type of a stress-strain curve. And the change from elastic to plastic is essentially the difference between these two models. In the first model, we have a very abrupt change. So we're loading up elastic and then we go kind of horizontal plastically, and then we continue to increase. And in this case, we're just gradually nonlinear. When the change is abrupt, the yield strength is usually given by this lower value here. You can see that it's not given by the peak value at point B. We're going to talk about several models now that are used to represent these two different stress strain curves. And the two of the four models are shown here. So when we do this modeling, we need to have analytical expressions for these stress strain curves. And in the figures above, it's really hard to come up with an analytical model for this stress strain curve or this one. And so what's been developed are models that are kind of bilinear. And so we break them up into components. And there's actually four of these. The first two models are shown here below. And the first one is what we call elastic, perfectly plastic. And so what happens here is during loading, we go elastic. Once we hit the yield strength, we go flat, we go horizontal during the loading. So the stress would not continue to increase, but the strain would continue to increase. So this is loading. Then as we unload, we drop back down in the unloading region, and we come all the way down here to point C and then over. So this would be what we would call an elastic, perfectly plastic model. In this model, we have elastic strain hardening. And what we allow to happen, or what we model, is the linear elastic region. But now instead of being perfectly plastic or going horizontal, we allow the material to strain harden and the strength to increase as we plastically deform. So the stress would also increase. Then as we unload, we would drop back down and come down and have some plastic deformation and go into compression. Now, these solid lines we can come up with equations for and analytically model. It's important to note that the material usually follows this dashed line. And so you can see the differences between the analytical models and what really goes on in the materials. In these cases where the materials don't follow the models in this unloading region, this is kind of often referred to as the Boschinger effect. And we'll talk about that. Another note or a little more detail on this Boschinger effect is this occurs when a material increases in one particular property as it decreases in another. And this effect is prevalent in the tensile and compressive yield strength as shown on the previous pages. So you can see here that we increase the yield strength in the tensile region, but here in the compressive yield strength it decreases. And that is referred to as the Boschinger effect. The other two stress strain models that we use for materials experience loads that put them well into the plastic region. In these cases, the elastic strain is small compared to the overall strain and is typically neglected. So when the elastic strain is neglected, it's said to be a rigid material. So the other two common stress strain curves that we are going to model go vertical, and there is no elastic deformation. And so, for example, this first one we would call rigid, then perfectly plastic. And this second model we would call rigid and then strain hardened. And they're different than these cases where we had elastic and a slope line, and then either perfectly plastic or strain hardened. So those are the four models that are typically used when analyzing and using equations to represent a stress strain model. Okay, with that review, let's go ahead and start talking a little bit more about plastic design. In axial and bending loads, the plastic region is analyzed quite differently. For example, in most engineering design, you guys have been exposed to failure when it's determined by the largest stresses on the cross section and when they hit the yield strength. And then we're done. In axially loaded members, the stress is given by sigma equals P over A. And the stress is uniform throughout the entire cross section. And so in that situation, the entire cross section would become plastic at the same time. That is different than bending. In a bending load, we know that the stresses are largest on the outside of the beam. So in MC over I, the stresses are largest where C is the greatest. And the stress distribution is not uniform, but it's linear throughout the cross section, with the largest stresses being on the outside of the beam. So in purely elastic theory, the beam would be failing as soon as the outer fibers of the beam have reached the yield strength. And this often will cause a structure to be way over designed, way too big. Because what can actually happen is that outside part of the beam can go plastic and still not fail. And so we can allow a portion of the stresses on the outside of the beam to go plastic and carry more load before the beam actually fails. And this is what we're going to focus on in the remainder of this section, is how do we analyze that? How do we let the or how do we know the amount of plastic deformation on the outside of the beam that we can handle before the beam will completely fail? And the computation of this is what we are going to talk about in the remainder of this section. So to start off with, let's talk about our assumptions. Our first assumption is that the material follows an elastic, perfectly plastic model. So going back to the analysis that we've talked about, that is this case here, where the material would be elastic and then perfectly plastic or go horizontal. So once we hit the yield strength, there's no more increase in stress, but there's an increase in strain. So that's probably the largest assumption. And this is actually a really good model for mild steel. For some other materials, it doesn't work as well. But for mild steel, this model is just fine. We're also going to assume that the yield strength is the same in tension and compression. And we've seen from some of the models before that that is not true, that the compressive yield strength becomes less. But we make the assumption that they will be the same. We're also going to assume that transverse cross sections remain plane so that the strain is proportional to distance from the neutral axis. However, in the plastic region, we're going to assume that the stress remains constant and is not proportional to the distance from the neutral axis. So this is a big difference here, and we'll talk a little bit about this assumption in the following pages. So to kind of help illustrate that last assumption, we have this figure here. And this first region shows how the strain in a beam is linear. This would be the neutral axis of the beam coming through here. This would be the top of the beam and the bottom of the beam. We see that the strain on the bottom could be tensile, and then on the top would be compressive. We also see that the stress is linear through the beam. So this is what occurs in the elastic region. This is what you're used to computing. This is MC over I. Now, if we let the beam go partially plastic, the strain, we assume, continues to be linear. Here you can see that the strain has been increased beyond the elastic region, and it continues to increase, but that it is linear through the beam. However, the stress, once the stress hits the yield strength, it does not continue to increase, but it hits a maximum value and stays constant. And so that maximum value in this example has been reached down to this portion of the beam. So this has all hit the yield strength. This region in here, where the stress is still lower, is still in the elastic region. And then down here on this side of the beam also, we have hit the yield strength limit. Now, when we go fully plastic, this is called the fully plastic state. When we hit this state, we call it a plastic hinge, or sometimes it is referred to as a plastic hinge. This strain, you can see, we have assumed is still linear, and it continues to increase. So your beam continues to deform. It continues to stretch and plastically deform. However, the stress in the beam hits a maximum value and then stays constant. Once we hit this plastic hinge value or stress state, the beam would just fold in on itself and completely collapse because it could take no more stress, and the strain would just increase rapidly and the beam would completely fail. Once we hit this state where we are fully plastic, or a plastic hinge has been created, we call that point the fully plastic moment, MP. And in bending, it's the moment required to cause yielding in either tension or compression throughout the entire cross section. So once we hit our plastic moment, that is the maximum moment the beam can carry before it completely fails. And we can come up with expressions for when this plastic hinge or this plastic moment has been developed. The basic approach is to determine an expression for the maximum elastic moment, which we're going to refer to as My, and then the plastic moment, MP, can be obtained. And we often refer to the ratio of MP, the plastic moment, over the elastic moment as the shape factor. And for most common cross sections, this shape factor value can be looked up in the steel construction manual or other manuals. And so the shape factor is the ratio of the fully plastic moment over the elastic moment. So given the shape factor S for a cross section, the plastic moment can be calculated, and from the plastic moment, the applied loads can be determined. So what we're going to do now is continue this by looking at computing the shape factors for various cross sections so that we understand how they are computed.